Welcome. In this brief video, we will introduce the median, how to calculate it, and a couple of ways to interpret it. The median is a measure of center, a measure of central tendency for a data set or a distribution of data. In particular, it is the middlemost value in the ordered data set. And this part of the definition needs extra attention. The data set must be ordered. In fact, this is the very first step to finding the median. Sort the data set in order. There are a couple of ways that this can be accomplished if you have your data in Excel or Google Sheets. While there is a sorting button or a graphical user interface option that is available if your data is all in one column, I prefer to use the syntax/function features in Excel to sort my data. The nice part about this approach is that the data does not need to all be in one column to sort the data, but the function approach will put the data all in one column in sorted order. Here I will demonstrate the small function to put the data in ascending order. There is a comparable function, large, to put the data in descending order, but I won't be presenting that here. So for now, we will focus on the small function only. I will show the simplified approach that only requires that the first appearance of the function is in row 1, and then copy down until all the data is sorted. Let's assume the data is the only information in columns A through E, not necessarily filling the entire columns, but there is nothing else in those columns but the data. In place of the position argument, we will use a function that automatically counts for us, namely the row function. We'll explain this a bit more shortly. Let's skip column F so as to have a blank column between our raw data and the sorted data. In cell G1, we will type equals small, open paren, A:(E) to select the first 5 columns, comma, row, open paren, close paren to close the rows function, and close paren to close the small function. Then, once this function is entered in cell G1, we will copy this down column G for the number of rows representing the sample size of the data set. Let's break this formula down briefly. The first argument is the array or location of the data. In this case, we are telling the function that our data is in columns A through E. The second argument asks for the ranking for the number in which we are interested. Had we entered the function equals small paren A:(E), 1, this would return the smallest value in the data set, the minimum of the data set, if you will. Likewise, equals small A:(E), 2 would get the second smallest number in the data set. Small A:(E), 5 would give the fifth smallest number. So instead of typing 1, 2, 3, 4, 5, etc. all the way down up to however big the sample size is for our data, we will take advantage of a function that counts naturally if we copy it down the column, and that is the row function. The key here is that you must start in the first row of your column for this to work. If you decide not to start in the first row, you need to use a variation of this syntax. Let's say you really want to start the data in the 5th row of column J, in other words, in cell J5. So in the first cell, J5, you should use the following syntax. Equals small, open paren, A:(E), the location of the data, comma, row, open close paren, minus row, open paren, absolute reference for J5, that's what the dollar signs are for, close paren, +1, and then close paren for the small function. To clarify, $J, $5 represents the absolute reference for cell J5, which is the first cell in which you want the sorted data to appear. Then copy this down until you start to see errors being returned. Here's a quick demonstration of this using a small data set in Excel. As you can see here, we have a small data set in columns A through E, the first 5 columns. We're going to use the small function to put the data in order. So I will enter equals small for the function, open paren, A:(E) to select everything in the first 5 columns. Again, just noting that there's nothing else in these columns except the data, or else I couldn't use this function, comma, and now to count through the values 1, 2, 3, 4, etc., I'm going to use the row function because as I copy this down each row, that function will update. And I'll use a close parenthesis. Now, that gives me the first value in the data set, the smallest value, because row for this first row is the value 1, and that would be the smallest value. I'll use the formula text function here to show what's actually in that cell. Now I'm going to copy this cell, and I'm going to drag this down a little bit further than I know that is in the total data set. And you'll see as it's given the data, once you hit the end, it's going to start throwing out some errors. Well, I know that that's because there's only 15 values in the data set, so if it tries to find the 16th value, what you would be getting if you had the row function in row 16 is asking for the 16th value of the data set, well, there's nothing, so I'll just go ahead and delete those. Again, if for some reason I wanted to start my function in J5, instead of starting in row 1, the method I just showed really only works if you started in the first of the rows. I could do the same thing here by saying small a colon e, and now I'll say row minus row, and I'm going to give the absolute reference for the cell in which I'm currently located, the first cell for this ordered data set, J5, and then I'll say +1. And now the row function is going to do the same thing as it counts up, but it's always going to start counting from 1 going up. Again, I'll use the formula text function so you can see what was entered there. Now, if I copy this down quite a bit, if I copy this down a bit, it'll go until we hit an error. And once I start hitting the errors, I know I can go ahead and delete those because those are beyond the length of the data set, and that actually sorts the data set. And that's the useful demonstration on how to use the small function in Excel. Okay, so recapping, the first step is to sort the data. The second step is to find the middle of the data. More precisely, we are looking for the value or values that separate the lower half of the data set from the upper half of the data set. Sometimes this will be a precise single number, sometimes not. Let's work through a couple of examples to demonstrate the two possibilities we might encounter. We will work with the first 9 odd prime numbers. 2 is the first prime number, but we will not include that because it's not odd. The first odd prime is 3, then 5, then 7. Next, 9 is divisible by 3, so it is not prime. 11, 13, 15 is divisible by 5, so not prime. 17, 19, 21 is not prime. 23, 25 is a perfect square, so not prime. 27 is a perfect cube, so not prime. 29, and I believe that is the first 9 odd prime numbers. 3, 5, 7, 11, 13, 17, 19, 23, and 29. First, we note that our data is already in order, so we are good to go there. So we just need to find the middlemost number in the sorted data set. And the middlemost would be here at 13. That happens to be the 5th number in the data set. We notice that there are 4 values below this number and 4 values above this number. So that is indeed the middlemost number. The median for this small data set of 9 values is 13. Now, let's find the median of the first 12 odd prime numbers. The next prime would be 31. Then 33 is divisible by 11. We'll skip it. 35 is divisible by 5. Skip it. 37 is prime. 39 is divisible by 3. Skip. 41 is prime, and that gives us the first 12 odd prime numbers. Again, our data is already in order, but now if I want to find the number that is in the middle, meaning there are the same number of values above and below that value, unfortunately, there is no single number that would work because we have an even number of data values. We could divide the data in half here between 17 and 19, which would give 6 numbers below the breakpoint and 6 numbers above the breakpoint. However, there is no single number within the data set that would work. So what we do instead is to take the two middlemost values, 17 and 19 in this case, which ends up with 5 numbers below this pair and 5 numbers above this pair. So it is not a single number that is located in the middle of the data, but 2 numbers located in the middle. Next, we will take the average, or halfway point, between these two numbers as the median. The average of these two is 18, which is both even and not prime. Thus, as with the mean, it is possible to obtain a measure of center that is not even a value in the data set. To summarize, the median for the first 9 odd primes is 13, a value in the data set, and the median for the first 12 odd primes is 18, not a value in the data set. The takeaway message here is that we have to do something different if there is an even number of values in the data set as opposed to when there is an odd number of values. If the sample size is odd, we add 1 to n and divide the sum by 2. The value in the sorted data set at that position would be the median. If the sample size is even, we divide n by 2 and then take the number at this position and the one immediately following it. The average of these two numbers is the median. Here are a couple of quick observations about the median. First, unlike the mean, the median is a resistant measure. This means if our data set contains extreme values at either end of the data set, the median is not impacted by these values. Why? Well, if I'm only focusing on the middlemost one or two values, then it really doesn't matter what happens with those extreme values. But there's a consequence for this. The protocol for the median is rather simplistic. The median calculates the value by purposefully ignoring a large part of the data. We say that the median is very uninformed by the data set because it uses the value of only one or two values from the data set in the calculation. Let's say there is 1001 values in the data set. The median looks at the middlemost number and ignores the other 1000 values. It ignores a whole lot of the data. Recall, the mean utilizes every value in the data set when you calculate it. The median does not. Again, we say that the mean is a well-informed measure of center and the median is an uninformed measure of center. The flip side is that the mean is not resistant, but the median is. Now we will briefly introduce the concept of the percentile, because the percentile is another tool we might use to calculate the median. In fact, the median is actually the 50th percentile. You've probably heard the concept of percentile used before. For example, you may have heard someone say, my SAT score is in the 88th percentile, or some version of this. The way we interpret this is as follows. A score is in the 88th percentile if 88% of all SAT scores are below that score. In truth, it probably is better to say that at least 88% of all SAT scores are at or below that score. The reason we say at least 88% and at or below is because we may have repeated values in our data set. We will explore the need to use language like this to hedge our bets shortly. Briefly, it could be the case that 88% of the values are strictly less than and 91% are less than or equal to. Again, we'll explore more on this shortly. Well, the median is just the 50th percentile. This is the value where at least 50% of the data is at or below this value. Using our former definition for the median, the middlemost number in a data set, we see that these definitions should produce the same result. Unfortunately, they do indeed give the same value. In the next video, we will explore this briefly with a data set while we formally introduce the protocol to find any arbitrary percentile for any given data set.